All right, so hello everyone. We will get started in just a couple minutes. Alrighty, so good afternoon, everyone. My name is Rory Bentley. I'm a graduate student here at UCLA and one of the coordinators of the UCLA Planetarium. So tonight's topic is very relevant to both kind of current news in astronomy and the research done here at UCLA by the UCLA Galactic Center Research Group, of which I am a part of. So for starters, just a little orientation. As you can see on the title, we're going to be talking about our galaxy's core, the Galactic Center, as it's usually called, and the 2020 Nobel Prize in Physics. It'll just be a kind of a general cover of all of that and kind of describing how everything is related. So, let's go get started. For starters, let's talk about where the Galactic Center is in relation to us. So, the Galactic Center, you can tell by its name, it's located at the center of the Milky Way galaxy. Now, the Milky Way galaxy is a very big place. It's about 100,000 light years across, and we're about 26,000 light years from the center of the Milky Way. Now, it's a big number, but what does that mean? Well, a light year is about 6 trillion miles, so it's a very long way away. The sun is about 8 light minutes from the Earth, so not that far, and the nearest star to the sun is about 4 light years away. So the Galactic Center is a long way away from us, from the solar system. Now, there's one small problem when we're studying the Galactic Center that's sort of going to be really important to a lot of kind of the early parts of this talk. We actually can't see it with conventional telescopes. That's because the Milky Way is a very dusty place. There's huge clouds of dust that block us from seeing the Galactic Center. And you can see that in this image. So this is a visual light, so light that our eyes can see, image of the kind of Galactic Center region, with the location of the Galactic Center indicated by this red arrow. Now, you can see it's pointed right at this big black stripe that cuts across the image. That's one of those massive dust clouds. And for a long time, no one could see through it because, there's just nothing you can do. You can't just go to the other side of the dust cloud because space is enormous. So, to solve this problem, astronomers had to come up with some other kind of clever trick to see through 26,000 light years of dust. What we do is we just use a different type of light. So, what do I mean by that? Light is the photons that make up light. they actually have a little sort of wiggly wavelength to them. They're both a particle and a wave. You don't need to think too hard about this, but the different wavelengths of light interact with matter in kind of different ways. We can only see a small range of wavelengths of light. We call this the visible range. But there's a whole bunch of other types as well. Some of them you may have heard before, like the X-ray. An X-ray is a very, very short wavelength of light, and microwave and radio waves, which are much longer wavelengths. And some of these types of wavelengths can actually pass through the dust unimpeded. And they will give us a very clear kind of image of what we can see in the galactic center. Or of the things in the galactic center, I should say. This image, this kind of collage, shows the galactic center as viewed through 4 different wavelengths. And you'll notice that in a lot of them, the galactic center looks very different, especially between, say, the microwave and the near-infrared wavelengths. That's because these different types of kind of light, they're actually emitted and interact with different types of matter, or different kind of objects in space, not types of matter. For the microwaves on the top, they're primarily emitted by, say, kind of cool dust and gas. Infrared, so the second from the top, is emitted by nebulae, warmer gas, and a lot of these kind of nebulae that you see in the infrared are places where stars are being born. The near infrared, which is the shortest wavelength that we can see here, that we can see into the galactic center with, is primarily emitted by stars. And you can kind of see that the cloudiness in the microwave and the infrared isn't quite as apparent in the near infrared. And you're starting to see dusty filaments creeping in as the dust starts to block some of the near infrared light. At the bottom, we have the visible, where we can't really see anything. Another problem with observing the galactic center is it's a long way away. This is an unfortunate problem, as the galactic center is a really unique place in astronomy. It's the only center of a galaxy that we can observe in any detail. And because it's so far away, it makes observing it really hard, because it's a pretty tiny place in the sky, and since it's far away, it's going to look really small. But we have to deal with that, because the next nearest galactic center that's kind of even remotely comparable is in another galaxy 100 times further away. This means we need to use the biggest telescopes that we have to study the galactic center. In this picture on the right, or on the left, I'm sorry, you have a tiny white circle marking the approximate size of the kind of the innermost portion of the galactic center compared to the full moon. The full moon is not very big on the sky, actually, if you kind of go out and kind of look at it. So this point is extremely tiny, and we want to see details within that point. So we need a huge telescope. The biggest telescopes that we have available that are best suited for these studies there's only a few in the world. Two of the kind of the best suited ones are the twin Keck telescopes on the summit of Mauna Kea in Hawaii. Those are pictured on the right. Now, this is where UCLA comes in. UCLA has been one of the major kind of players in the development of the Keck telescopes. When they were brought online in the mid-90s, people had already recognized that they would be very useful for studies of the Milky Way's galactic center. Their massive size and their very great location in the world meant that they were really well suited for galactic center studies. And so in the kind of the mid-90s, 3 UCLA astronomers, Andrea Ghez, Mark Morris, and Eric Becklin, formed the UCLA Galactic Center Group. The GCG has been studying the galactic center since then for over 20 years, using primarily the two Keck telescopes. So, 20 years is a long time to study anything in astronomy. And so the galactic center is a very busy place, and so we've probably found a whole bunch. We've definitely found a whole bunch. I should know that. So what have we found? Well, first of all, the center of the galaxy is one of the densest concentrations of stars known. This picture shows the nuclear star cluster, which is the cluster of stars that surrounds the exact center of the galaxy. This is an actual picture from, I think it's from the Keck telescopes. There's two labels on here. First is this label in the center, which says there's an arrow pointing towards something, the center of the cluster, with this Sgr A star. That's short for Sagittarius A star, and that's the location of a radio source at the very, very, very center of the cluster. This, on the bottom here, you have this kind of key, this kind of bar. This marks the distance between the sun and the nearest star at the distance of the galactic center. And you can see, because basically all the stars in this image are in the galactic center, there's a lot more stars, or the stars are packed very, very close together. Much closer than the kind of the distance between the sun and our nearest neighbor. Keep in mind, or sort of one thing to note in this image, is that we're actually only seeing the brightest stars in the galactic center in this picture. There's even more stars that we can't see that are just too small to kind of make out. And so, in reality, the galactic center, the nuclear star cluster, is even denser than this image shows. Studies over several years also produced this video. Now, what we're seeing here is just a zoom in on the very center of the nuclear star cluster. And you can see there's a bunch of different stars down there, and they're all moving. Some of them are moving in nice little... Hold on a moment. Sorry. Excuse me. Okay. Let me just bring this back up. Okay. Sorry, there's just a little glitch on my end. Not quite sure what happened. So, I'm going to keep going, and if I get, if I disappear, someone, like our chat moderator, will let me know, please. So, you can see in this image that there are kind of a collection of stars that appear to be moving around something. Now, if you look at what they're kind of circling, there doesn't appear to be anything there. Now, these stars are moving very fast, and so in order to accelerate a star to such speed, you need to have something very big. But you can't see it. But you can't see anything in this image. So, you need to have something very big, but also invisible. Okay. One of these stars is accelerated so fast it reaches about 3% the speed of light, or 5,000 miles per second. This star, which is shown in the yellow in this video, we call it SO2. And you can see it takes about 15 years to orbit if you kind of clock it from the observation dates that you see in the upper corner. Now, in order to have something that can move a star so fast, be invisible, but also be small enough to not hit the star, there's only one object in astronomy that can do that, and that is a huge black hole. So this kind of observations of this star, SO2, was used to determine by the UCLA Galactic Center Group that at the very center of our galaxy, there's a 4 million solar mass black hole. Which means it's the amount of stuff, the amount of matter in this black hole is 4 million times that of the sun. We call this black hole Sagittarius A star, and it marks the exact center of the galaxy. It's sort of the glue that holds the rest of the galaxy all together. Now, I mentioned that it's invisible, but it's not really, because things, when they fall into a black hole, before they kind of hit the point of no return and we stop being able to see them forever, they get ripped apart and heated up. When they heat up, they start to glow. And so one thing that we've been able to do over the years is observe kind of asteroids and comets falling into the black hole. They fall in, they get ripped apart, and they start to glow. And we can see them do their sort of last dive before falling into the black hole as little flares. They can last anywhere from a few minutes to a few hours. And we can see a few of them in this little video. The black hole is this little red kind of flashing dot. And this was taken over the course of just one night. Usually these flares last maybe an hour or so. Okay. But the black hole is not the only interesting thing in the nuclear star cluster. The nuclear star cluster itself is a very weird place. One of the kind of important discoveries I like to think it's important because I've worked on it, is the discovery that the stars appear to come from a whole bunch of different places. When you look at what stars are made out of, that can tell you a lot about where they came from. Stars formed in different places will have different chemical compositions. And when we look at most of the stars in the galactic center, they kind of resemble the usual star that you see in the Milky Way. There are some weird things about them, but their sort of bulk composition is pretty similar. However, we also see that there is a small population of stars, that appears to be kind of different from most other stars that we see in the Milky Way. And these stars resemble stars that we see in other much smaller galaxies more than other Milky Way stars. What we think happened was billions of years ago, there was a smaller galaxy that was captured by the Milky Way, which is a very big galaxy, and then the Milky Way's gravity actually kind of ripped the smaller galaxy into kind of a cloud of stars, absorbed a whole bunch of them, and then those stars eventually migrated into the galactic center where they got stuck. And that's where we see them today. So that's sort of a very interesting find, finding stars from at least somewhere very different from the galactic center, all concentrated into this one place that really we weren't expecting to find them. Just as interesting was the discovery, which was actually took place much before the discovery of those kind of extragalactic stars, was the finding that many of the stars in the nuclear star cluster in the galactic center were very young. This caught a lot of people by surprise because it was expected that kind of the presence of any huge supermassive black holes would rip apart any nebulae before they were able to form stars. Essentially, you couldn't have stars form in the galactic center. And any stars that you saw down there would have formed much further out and over long periods of time migrated inwards to where we see them today. But we see a whole bunch of very young stars when we look at the galactic center. All the stars marked with red X's in this figure, those are all young stars. Now, these are not just like young stars, but these are very young stars. So they had to have formed pretty close to where we see them today. Exactly how they formed, where and how they got to where they are today is not very well understood, and we're still it's still an open question. Additionally, there was in the past decade, there was the discovery of a few of the what we call G objects. Now the G objects, they look just like little pom-poms of gas flying around the galactic center. They have little orbits. They're not quite like stars. They're sort of fuzzy looking, rather than looking like little dots. And we've found about 6 of them and have been monitoring their orbits since. Now they're not really like anything else we've seen in astronomy. What we think they are, though, is that they're essentially the debris clouds from the collision of 2 stars in the very dense environment of the galactic center. Essentially, you have 2 stars ram into each other. They fuse, but also spray a bunch of gas out from their collision. And what we think we're seeing is that gas cloud that formed around the stars when they collided. And we think that there's probably a fused pair of stars in the very center of that cloud. Again, we're not quite sure what's going on here, but it's something that we're researching through even as we speak. Another to change gears again, one of the advantages of studying one specific aspect of astronomy or one specific object for such a long period of time in such a consistent manner, we've been essentially doing the same thing every year, it means we have a pretty good idea about a lot of the objects down there, like how they move, how they interact, how they move, how they behave, things like that. And this means this is especially useful for monitoring the orbits of the stars as they orbit the black hole. This animation just shows you the orbits, or all the known orbits of stars around Sag A star, the black hole. And we're pretty confident in a lot of these. And so having a good idea of how the stars move, that's really useful for conducting a bunch of experiments, understanding what they're doing. Come on. So this huge, long period of observations was used to great extent about 2.5 years ago, when SO2, our favorite star that swings right past the black hole, made its closest approach to the black hole in 2018. Now, this presented an opportunity to do a really cool physics test that had never really been conducted before in astronomy. And what we're doing here is actually testing Einstein's theory of general relativity. So general relativity, the prediction says that as the star swings closest to the black hole, as it gets very, very deep into the the black hole's gravitational field, the gravitational pull of the black hole will actually distort the light from the star and actually cause it to change color slightly. And so we set out to detect that. And so in 2018, the star swung close to the black hole, and we were observing all the summer when it made its closest approach. And sure enough, when we combined our 2018 observations with our kind of extensive knowledge of the star's kind of behavior from our previous observations, we were able to detect the predicted shift by general relativity, and we found that, well, Einstein appeared to be right. So that was a really cool, really fun kind of experiment that we did. And it's one of the main reasons why just last October, the Galactic Center Group's kind of team leader, Andrea Ghez, was one of the recipients of the 2020 Nobel Prize in Physics. She received this, one of the big motivations was the general relativity test in 2018, but really it's for all the discoveries before that as well. So she's sort of spearheaded the Galactic Center Group since its formation back in like the mid-90s, and has been behind a lot, in fact, basically most of the discoveries we've talked about today. She also shared the prize with theoretical physicist Roger Penrose, who has done a lot of kind of theoretical physics around black holes, along with Reinhard Genzel, who's an astronomer who leads a very similar group to the UCLA Galactic Center Group based in Germany. They also study the Galactic Center using kind of similar telescopes in South America. So that brings us today to, that's sort of a good kind of ending point as to where we are today. But we have a lot of things to look forward to in the future. So in kind of the next few years, we have something called the Event Horizon Telescope to look forward to. Now, the Event Horizon Telescope is it's sort of a combined project between a whole bunch of radio telescopes across the world. Radio telescopes can do this kind of really weird thing called interferometry, where you basically combine the signals from telescopes all over the world to make a much kind of a much bigger image. You can essentially combine telescopes across the world to make a telescope as big as the Earth itself. It's complicated. You could do an entire lecture on that. I'm not going to cover it, don't worry. But basically, they're using the combined telescopes to attempt to photograph the shadow of the black hole, essentially the point of no return. Even with the massive telescopes, all we can see is just a little dot. What they're trying to do is trying to resolve the black hole itself, see things falling in, like you see in this simulated image on the right, where you have this kind of clear spherical ball that marks a simulated image of Sagittarius A star as seen by the EHT, the Event Horizon Telescope. Additionally, in the future, the Galactic Center Group has a whole bunch of things that we're looking forward to. We have more physics tests in the future that you can only do in the Galactic Center, along with a whole bunch of projects pertaining to the origins of the stars down there, things like that. Additionally, we also have telescope upgrades to look forward to. So in this little animation, you have 3 panels. The one on the right, or on the left, excuse me, that shows essentially what a simulation of what the Keck telescopes see today. You can see it's kind of smudgy images of stars. We're really pushing the limits of what the telescope can see. However, there's also instrument upgrades on the go for the Keck telescope. With those, we'll be able to see what we see in the middle panel. This upgraded telescope will be able to see stars even more clearly than we see today. Many of these kind of instrument upgrades will come online in the next decade or so. Finally, for the decade after that, we have the panel on the right. Now, the panel on the right is a simulation of what the Keck's successor, the 30-meter telescope, is expected to see in the Milky Way's galactic center. And you can see it can see many more stars much clearly than either of the 2 Keck telescopes. This is the TMT, the 30-meter telescope, is expected to come online in the next decade or two, so it's still a long way in the future. However, we have a lot of work to do before then, and with that, I will wrap up and take questions. Hold on a moment. I need to... okay. Let me just get to my... Okay. So if you have any questions, just post them in the chat. Okay. So if you have any questions, just post them in the chat. Yeah, I may have lost a couple of them on the chat. So if you maybe posted it a couple minutes ago, I might not be able to see it. Or I won't be able to see it. Apologies for that. So if you have any questions, just post them in the chat. Yeah, I may have lost a couple of them. Okay, well, if there is no questions, well, thank you everyone for showing up, and I hope everyone has a wonderful night and enjoyed the show. We're having these monthly we're having them Wednesday nights monthly. I think the next one is, I want to say it's February 17th, maybe 15th. So stay tuned for that. I believe it's on how to photograph an exoplanet, and it'll be given, I believe, by Briley Lewis, who's one of our best presenters. So definitely show up for that one. Thanks everyone for showing up again, and hope y'all have a great afternoon.